So good afternoon, everyone. Again, my name is Daniel. I'm a solutions architect at Isovalent, and this will be my talk about eBPF and how it can help us secure a cloud-native environment. So I'll talk really quickly about what eBPF is. We'll kind of motivate it, why, or what problems that it'll help us solve. We'll kind of do a little bit of an overview about all its different components. And then we'll go through kind of an example eBPF program. We'll actually look at the different components of what it takes to get an eBPF program written, what it takes to get into the kernel. And then after that, we'll kind of go through some applications for it, specifically in networking and security, runtime security, observability. And then if you're down, I'll assign you a little bit of homework at the end with some practical apps. So quickly, again, my name is Daniel. I work on Cilium, Tetragon, Kubernetes, CNCS stuff all the time at Isovalent. That's my LinkedIn down there if you want to be friends. Okay, so let's get started. So the Linux kernel. So it forms kind of the foundation of the Linux operating system, which forms the foundation of everything from cars to servers, fridges, TVs. It powers essentially most of the widely used technologies that we have today. But all of them kind of intersect at the kernel. But what is the kernel and what does it actually do? So the Linux kernel is a software layer between our user space applications and the actual hardware where things are actually happening. So when we want to write to disk, when we want to read from memory, when we want to do anything with the network stack, it's got to go through the kernel. And the way that our user space applications will call our kernel functions is through something called a syscall. And on the right here, hopefully. And on the right, you can see all the syscalls that get called when I just simply try to echo hello world to the screen. So there's quite a lot of things that go on just to do a very simple task. It's not uncommon to kind of require new features to Linux, but adoption can be quite slow, right? Traditionally, if you wanted to build a new, let's say, observability tool for your application, well, you'd have to write it in a way. If you want to write it into the Linux kernel, you have to write it in a way that benefits the entire community and then advocate for its adoption. And then if you pass through that filter, it's got to get onto a kernel release. And then once it gets onto the kernel release, it has to get onto a distro. And then your company has to adopt that distro, move it to production, right? So that could take like years. You could also write a kernel module, but that's not without its own risk, right? A kernel module is something that gets loaded straight into the kernel. If it crashes, that brings down the entire system. And so the assurances that we had with kind of our long acceptance process that gets reviewed by a lot of people is essentially skipped. And it's all up to the kind of the kernel developer to make sure that module is stable and secure. And so this sounds pretty hard and pretty complex. So that's why kernel development has been relatively slow over the years. So that's where eBPF actually comes in. So these are little programs that run dynamically. It can be loaded and unloaded from the kernel. They are kind of attached, we'll say, to an event and then triggered when that event is observed in the kernel. So this kind of program enables a much more kind of dynamic process. One way to kind of think about it is the effect that JavaScript had to kind of our web pages. So early days, our web pages were quite static. And nowadays, they're very dynamic. They run some of the most dynamic, powerful apps in the world. And this analogy was first actually kind of coined by Brendan Gregg, one of the more influential people within eBPF. He says, JavaScript lets you define mini programs that run on events like mouse clicks, which are run in like a safe virtual machine in the browser. And with eBPF, instead of a fixed kernel, you have mini programs that run on events like disk.io and are run in a safe virtual machine in the kernel. All right, so that's kind of how we got here. That's why we need eBPF, let's kind of go over really quickly what eBPF is. So eBPF is event-driven code that runs in the kernel that get triggered when the kernel or application passes a certain hook point. Application state gets stored in data structures called eBPF maps. And eBPF programs can make function calls to predefined helper functions. And these helper functions can do basic things like generate random numbers, get the gain time. It can also help us grab values from our eBPF map. We can get the process information, we can get C group context, we can manipulate network packets, we can manipulate even forwarding logic as well with these helper functions. Okay, so we have our code. So how does it actually get onto the kernel? So eBPF programs are typically written in C and then translated into machine code or bytecode, by an LLVM compiler. That bytecode, there we go. That bytecode then gets loaded onto the kernel by the BPF system call, which gets made by, or which essentially gets called by another user space application. And from there, it passes through our eBPF verifier, which checks for kind of safety and stability. And if it passes through that, it gets compiled into machine code by a JIT compiler, so a just-in-time compiler. And then finally, it actually gets attached to our system call or the hook point that we want, that we defined earlier. And then every time that hook point gets called, we can run that eBPF program. All right, so that was kind of a bit overview. Let's kind of walk through an example. So for kind of the purposes of an example, we'll make a small, really simple eBPF program. This program will attach a kprobe at the entry of the exec VE system call. And then we'll populate a hash table that includes the user ID, as well as, I guess, an incrementing counter for the number of times that a user was observed to call the exec VE function. And this will essentially help us count how many times a user has launched a function. And we'll print that to the terminal. So that's the program we're going to write. All right, so let's begin. So we'll create, first thing we'll create is our BPF hash table. And we'll use this using a macro from BCC. First thing we'll do is we'll create a variable called counter. We'll initialize it to 0. We'll use the BPF get current user ID helper function to populate the user ID value to the UID variable. We'll do kind of a lookup in our hash table to see if we've seen this guy before. And we'll load that value into P. And if P is not empty, then we'll load that value into the counter variable. We'll increment the counter variable, and then we'll actually update the contents of the table. Cool, so we have our C code. So that will be the actual eBPF code that runs when exec VE gets called, but we need something to help us load it onto the kernel. And so in this example, I'm going to use a Python application. So our C code will kind of live inside that green ... I've just kind of condensed that there. This is the actual user space application that will load our eBPF code into the kernel. So quick walkthrough, we'll instantiate kind of a BPF object called B. We'll attach the C function we just wrote to the exec VE system call. So those are the two variables, right, arguments right there. And then every 2 seconds, we'll read from the counter table map, and we'll print those values to the screen. Now that we have our function, how do we get it onto the kernel? All right. So the first step is to actually pass through the eBPF verifier. So the first thing that it's going to check is to make sure that the process actually loading the eBPF program has the required privileges. It's going to make sure that the program does not crash or otherwise kind of harm the system. So it'll check things like register values are handled properly, memory access is done within defined limits. It'll check the pointers are handled properly, et cetera, things like that. Things that would cause a C program to crash. And then it'll also check that the program always runs to completion. Once that's all passed and we're all good there, we'll send it to the JIT compiler, which will translate it into machine code. And then finally, it'll be attached to the entry point of our exec-v syscall. And so when you run this, so this is an example of me running it. On the right, you can see kind of my DJC user. ID is 1023. I'll run 3 different programs, so who am I, echo, and PS. And you can see my the value on the right incrementing, so 1, 2, 3, 4. And then beside that is also the root user running a bunch of programs as well. Cool. So did everybody enjoy writing C? If not, it's okay. You don't need to be kind of an eBPF program to actually take advantage of some of the eBPF applications that are already available. So for example, within the CNCF, Cilium can help us do networking. Falco can help us do runtime security. BPF trace can do tracing. And there's also a bunch of SDKs available in a bunch of different languages. So Go, C++, R, Rust. eBPF programs can also understand our cloud native identities. So traditionally, networking is done in Kubernetes by like IP tables, but IPs are quite transient and not really useful for us when it comes to Kubernetes and observability. So with eBPF, we can have programs that are actually aware of the metadata that we actually care about. So things like labels, and we can use this data for observability and network traffic enforcement. And you don't need to make this translation in user space anymore. So I mentioned earlier Cilium. So Cilium is a kind of now graduated project within the CNCF. And this is kind of the family of projects within Cilium. There's Hubble for network observability. There's Cilium, which is the CNI. And then finally Tetragon, which does kind of the runtime security and observability and enforcement. Okay, so the first area that we can explore how eBPF can help us is within network security. So when it comes to networking, there's kind of a special eBPF program, type of group of programs or type of programs that are called, and they're called XDP programs. So it's kind of named after the XDP data path that the actual packets will take. So remember earlier, we talked about where eBPF programs can be run. It can be run anywhere within the kernel, and it can also be run within hardware drivers. That includes for things like NICs as well. That means we're able to kind of process packets even before they reach the socket layer of the kernel. And packets that would otherwise kind of take down our servers, either because there's a flood of them coming in or there's explicitly crafted to exploit a vulnerability or something like that. They can be stopped on the NIC directly without having to travel the entire network stack on the host. Yeah, that essentially unlocks a number of different use cases, one of which is DDoS mitigation. So for example, Cloudflare actually uses L4 drop, which is an XDP program right at the edge of their essentially data center servers. So that was kind of the overall life of a packet when it came to, and just go back. This is the life of a packet of something that would come into a Cloudflare data center and hit their server. But really the only part that we care about is right at the front. So at the bottom here, there's a XDP program there again called L4 drop. And it essentially receives telemetry and data from Gatebot. So this Gatebot is kind of the application that will load the rules for dropping essentially. It'll apply kind of mitigation rules to L4 drop so that it sees, so it knows what to drop right when it sees the packets. Yeah. Okay, so let's kind of see it in action. So this is kind of a graph that kind of shows a let's say, DDoS attack in real time. So if we look at the red line, you probably can't see the labels at the bottom, but hopefully you can see the colors. So the red line is kind of the received malicious packets. So we see right at the crest of the wave that our CPU in pink goes up as well. And down there at the bottom in yellow, we can see that we lost some packets. So this is before Gatebot kicked in and introduced a rule to drop all these packets. So eventually Gatebot does kind of catch up. It's able to process that, oh, we're seeing a bunch of malicious packets. Here's a new rule to drop them all. And it gets pushed to L4 drop, and that's where you see kind of the green line jump up. And we're kind of essentially dropping it as they come in. And overall, the CPU only jumps up at around 10% during this, and it's relatively stable. And crucially, I think there are not too many packets lost. Yeah, so that's how it can help us within networking and network security. So now let's look at runtime security. So when it comes to runtime security, especially within Kubernetes, once our pods are successfully launched onto our nodes, eBPF can kind of help us detect abnormal or malicious activity, report these events when they happen, or even better, prevent them. Typically, when it comes to runtime, we'll care about things like file IO, we'll care about running executables, we'll care about system calls, network traffic, changing privileges especially, and namespace boundaries. And all these are operations that we can instrument with eBPF. One of the ways that you might have already come across eBPF is actually with seccomp profiles. So seccomp profiles essentially act as a filter to what system calls that are actually allowed by the container. So this image that I'm showing you is the example kind of default Docker seccomp profile that gets applied, and it filters out by default 57 calls. And they're not essentially allowed to be called by this container. So kind of the most immediate follow-up question to this is also one of the biggest challenge. Like if you had to ask a developer what syscalls their applications are actually making, you're probably going to get a blank stare and a laugh and probably a shrug eventually, right? Like remember the syscalls that were generated by just echoing hello world to the screen. That's where a tool like Inspector Gadget can help us. So it uses eBPF to kind of generate a sample, or not sample, or yeah, it'll generate a seccomp profile for you after kind of you dry run your application. And then you can apply it to your Kubernetes. You can adopt it within your Kubernetes manifests, and it'll essentially generate the seccomp profile on the right over there. Now with seccomp profiles and other security solutions that instrument mainly on syscall entry, the most obvious limitation is that we can only enforce on that syscall entry. There are a bunch of other places in the kernel that we can instrument as well, but if we're only limited to syscalls, then that's what we got, right? Yeah, remember we can instrument on a bunch of different other places, on disk read, at the packet level, and so remember, so that's where a tool like Tetragon can help. So Tetragon is part of the Cilium family of projects. With Tetragon, we kind of get kernel-level visibility and enforcement, and it'll act on kind of stable kernel functions like fd install for file IO. We can instrument on calls that would indicate namespace boundaries being violated, and output all that telemetry to our observability stack, like Grafana or our SIMs. With Tetragon, we can also apply enforcement inside the kernel, issuing synchronous sig calls. For example, if we see a container escalating privilege, we can kill it immediately from inside the kernel. Traditionally, this would need to be done by feeding that signal back to a user space application, and then to, I guess, asynchronously make that issue that sig call to the application. So to show you how that works in action, on the left here, I have a tracing policy that I'll apply to our Kubernetes cluster. Tracing policy is essentially the configuration object for Tetracon, where we configure what call we want to instrument on, what actions we want to take. And then on the right here, I have my privileged pod. So essentially, I'll exec into it. I'll try to mount the host file system onto /temp. And you'll see that it actually got killed right away. And you'll see that it actually isn't mounted to /temp. And then at the bottom, you can see that the action was observed, the mount action was observed, and a sig kill was sent to prevent this action. So finally, let's kind of bring everything together with observability. So we've talked a lot about how eBPF can help us with network attacks and runtime attacks. It can also help us with detection as well. Observability is naturally made much simpler by eBPF. We can monitor our applications. We can monitor their runtime and their network activity directly within the kernel. We can get very low overhead tracing for things like network performance, network protocol use, things like that. And one project that builds observability from eBPF is Hubble. So Hubble is, you can kind of think of it as like a prettier TCP dump. Instead of getting IPs and things like that, which aren't too useful within Kubernetes, we actually get the pod names. We actually get things like policy verdicts. So at the bottom, you can see that a packet was dropped because a policy denied it. We can see which part of the cluster which part of the cluster the flow is on. So for example, in the middle, you can see the flow kind of hitting the stack and then going to the endpoint, and then going from the endpoint back to the stack. So it's essentially an observability tool that kind of lets us look into our cluster networking much deeper. If you don't prefer the CLI, you can also get this from the UI. The Hubble also comes with a UI that also includes a service map that will show you the different components of your application and how they interact. As we saw earlier, you can also get process level visibility. You can see kind of processes launching and exiting. You can see file IO actions, so file reads, file writes, and like earlier, you can see mount events and things like that. We can bring these two worlds together even. So on the left, you see within Hubble, you can see actually a process tree for a pod, a process ancestry tree for a pod. So with our crawler pod, we can see that a bunch of functions were launched, and those functions essentially were processes launched network connections as well to things like Elasticsearch, Twitter, and this random reverse shell. And we can take all that observability and push it to our observability stack. So for example, with Grafana, so the same network flow table you can grab in Grafana. The same thing with the process ancestry tree. Grafana, you can also see a bunch of metrics to monitor for abnormal behavior. For example, if we see, here we see kind of a graph that shows top destinations as well as TCP metrics. When we do detect abnormal behavior, for example, in kind of an HTTP request, we can drill down with traces to investigate exactly which component of our application is causing that abnormal behavior. And finally, from a network policy perspective, we can see which policies are actually being matched. Are they the L3, L4 rules that we set up? Are they the L7 rules that we set up, or are they matching kind of summary, allow all, deny all rules? Cool. So last part. So if you want to kind of check out more about eBPF, learn more, get hands-on, you can try out labs at isovalent.com. If you do complete these labs, you'll get kind of badges, to digital badges, to kind of reward your completion. The labs are organized into kind of a map. And if you kind of want to follow learning tracks and stuff like that, You can do that from labsmap.isovalent.com. If you don't prefer labs and you prefer to read, you can read Learning eBPF by Liz Rice. And you can also follow along with our podcast twice every month, newsletter, as well as our Slack channel. You can come hang out there too. All right, thank you very much.